So now we will see a more non-trivial Sharpe complete problem, which will be interesting because of its algebraic nature. Okay, so this will be a very basic problem inspired from determinant or inspired from matrices. So for matrix A, for an n cross n matrix over some field F, let us call the matrix A, permanent is defined as permanent is the following value. It is the sum of product of elements in the matrix, but very special elements. These elements will actually correspond to picking n locations, none of which share a row or a column. Okay, so they will correspond to what are called permutations. So I in n, ai sigma I over all the permutations. Okay, so sigma this sim n is the symmetric group, the group of symmetry on elements 1 to n, so the n factorial size, and basically from so I, if you think of I as indexing the rows of the matrix A, then it is just picking distinct columns and mapping it to the rows. Okay, so there are n factorial terms in the definition of permanent. So sim is the group of n factorial permutations of n. Now notice its similarity with determinant. So what is determinant? Determinant is of the same matrix, same expression with a tiny difference. Same expression, except the difference is that here we will put a sign after before the product. So that's the sign of the permutation. Okay, so this sign basically there are the symmetric group has half odd permutations and the remaining half even permutations. So they are divided into +1 and -1. And that's the sign you have to put here. You don't need to know the definition of odd and even permutations, but just remember that half of them will have negative sign, and that changes everything. Okay, so this is determinant and earlier thing is permanent. As an exercise, you show that determinant is in FP. Okay, give a deterministic polynomial time algorithm for determinant, although the definition has n factorial terms, yet it is in FP. So though it has n factorial terms with plus minus signs, still you will be able to give an algorithm, okay, using the symmetry of the group. And this is used everywhere, of course, in linear algebra and engineering. But what about permanent now? So coming back to permanent, nothing like this is known. Okay, the only algorithm known is essentially this definition. So that's exponential time. So we'll see that permanent is the hardest problem in sharp P. Okay, so first we'll show that permanent is in sharp P, and next we will show, which will be a longer proof, we'll finish it next time, that actually it's the hardest problem with sharp P complete. So it is at the level of sharp SAT. Okay, just like sharp SAT, we don't expect to find a fast algorithm. Similarly, permanent, we don't expect to find a fast algorithm. Yet at the same time, determinant somehow has a very fast algorithm. Okay, so that's a surprising mathematical fact and conjecture. Let me not say it's just permanent is a hardest, is one of the hardest. Okay. So first is what is permanent to do with the sharp P? So permanent for 0, 1 matrices is in sharp P. That's the first thing. Why is that? What is sharp SAT, sharp P to do with permanent? That's not immediately clear, but then you think about it in terms of guessing and design an NDTM which guesses sigma. Okay, the set of sigma, this symmetric group is huge, but once it makes a guess on sigma, then it can actually identify those entries, multiply the entries to get 0 or 1. Okay, so let's design that NDTM. So let A be 0, 1 matrix, n cross n. Permanent of A is the number of permutations permanent is number of permutations such that this product of those entries, n entries, is 1. So if you look at it in this way, then you see that this can be solved by an NDTM, polytime NDTM, where the number of accepting paths is the number of these sigmas. So permanent equals the number of accepting paths of the NDTM that given A guesses sigma. So number of these correct sigmas, which will be the number of ones, others are zeros, product will be 0. That is why we needed 0 or 1 entry. So that's Hence we conclude that permanent is in permanent 0 1 is in sharp P. And this 0 1 permanent, there are many results, but there is no fast algorithm known. So permanent 0 1 has applications in computational physics, and probability, there are also approximation algorithms known. We will not do that, but you can do it as an advanced topic if you want. Approximation algorithms for the real permanent 0 1 entries. It has interesting connections through mixing of Markov chains and such. So what we will do here though is that it cannot be exactly computed, or it is not expected to be computable in polynomial time because it's sharply complete. Okay, that is what we will show. And for that we need a graph interpretation of permanent. So let's do that. So given a matrix n cross n, view it as the adjacency matrix of a weighted digraph so directed graph, right? Think of the matrix as an adjacency matrix of a weighted directed graph on n vertices. Where are the weights? The weights are on the edges. Okay, and the diagonal entries you can think of them as loops, weighted loops on the vertices. Edge weight, think of it as an edge weighted digraph. And then, so let me maybe draw it. And there might be loops on these vertices. And on the edges there are weights. So that can be anything, field element. It can be -1, it can be 0, it can be -2, it can be 1, it can be 4, it can be -10. Okay, so these are the vertices 1, 2, 3. Okay, these are the vertices, and then you have the edges which are all weighted. So this can be represented by a 3 by 3 matrix, and there could also be these edges. It's a directed graph, so anything is possible. Okay, so overall you can count that there are 9 integers, 9 field elements written as a matrix. So next concept that we want to define is to do with cycles, but maybe the cycle doesn't cover the whole graph, it covers a part, and then look at a disjoint cycle and so on. So look at a cycle cover. So cycle cover C of this weighted digraph A is a subgraph having n vertices, each having in degree out degree 1. Okay, that's the main thing, that it just think of a subgraph which is a union of disjoint cycles. So for example, here it can be one there's the vertex 1, 2, 3, and the subgraph we are considering of in degree out degree 1 is, let's take the 0 loop and then take this loop. Okay, the 0 loop on 1 and the 1 minus 1 loop on 2 to 3 and back. So this is a cycle cover, and there are many such cycle covers you can see. Okay, there are 2 more such cycle covers. So C is a union of disjoint cycles right, like in this picture, union of 2 disjoint cycles, that's a cycle cover. And we define the weight of a cycle cover so weight of a cycle is defined as, weight of a cycle cover, this subgraph, right, this is defined as product of the weight of the edges in the cycle cover. Okay, so in particular, in this example, it's 0 times 1 times minus 1, which is just 0. So that we call the weight of the cycle cover. And why did we do all this? We did this to give a to interpret permanent using graph. It's actually permanent of the graph or matrix A is a property of the graph that A specifies, and it happens to be sum of overall cycle covers. So permanent of A is the same as weight over the cycle covers C. So do this as an exercise. Okay, this is to do with let me sketch it. The idea is basically cycle decomposition of permutation sigma. So say monomial A11, A23, E32 and A44 appears non-trivially impermanent. The permanent definition is via sum. So in the sum, suppose there is a term, product term corresponding to this permutation, which sends 1 to 1, 1 to itself, 4 to itself, but 2 and 3 it swaps. Okay, that's sigma permutation. So what is this to? We actually want to map it to a cycle cover. That's the idea. So how is that done? So in the digraph A, consider the cycle cover. So 1, 2, 3 and 4, these are the 4 vertices in the digraph, and the edges that you should look at is this loop with the weight A11, 2 to 3 with weight A23, and 3 to 2 with weight A32, and then again a loop on 4. So this has the weight same as this monomial we were talking about. So this has weight equal to that m. Okay, so this cycle cover contributes this much weight to the right hand side, right, of this equation that we were considering, and it matches with the definition of permanent of A. And conversely, so every monomial in permanent on the left hand side has a cycle cover in the right hand side contribution, and every cycle cover corresponds to a conversely weight of a cycle cover of A corresponds to a monomial of permanent A. Okay, this is given by cycle decomposition also. Okay, so this is really a connection between the cycle decomposition of permutation. So its permanent is defined by via permutations. Every permutation gives you a cycle cover. Every cycle cover gives you a permutation. So that is what we have written here. So just check that, and that proves the equality, that permanent is the same as sigma over weight of cycle covers. Let's see an example of this observation. It's an important observation. So let's consider the matrix A 0 1 1 minus 1 0 1 minus 1 minus 1 0, and in the graph form it is vertex 1 2 3, the edges are So basically, what's the edge from 1 to 2? What's the weight of that, right? So that is 1, and then 2 to 1 is -1. What's the weight from 2 to 3? So that's the 2, 3 entry of the matrix. That's 1. I'm sorry, opposite direction. 3, 2 is -1. 1, 3 is 1, and 3, 1 is -1. That's the graph of this matrix, weighted digraph. And let's now list the cycle covers. So how many cycle covers are there? Basically, since you don't see any self loops, you have to use these. You have to use 3 edges, right? So once you can go clockwise or anti-clockwise. So there are 2 cycle covers. So first is this, and another. So let's write the clockwise one or anti-clockwise one. So this is so 2 to 1 is -1, 1 to 3 is 1, 3 to 2 is -1, 1 to 2 is 1, 2 to 3, and 3 to 1. Right, this is clear. And so the weight of this cycle cover is, this weight is 1,